Most games relevant to networks have very many players. Till now, we focused on two-player games just to define Nash Equilibrium and understand strategies. But the same concepts apply in games where have a large number of participants in social networks that we can think of often as a game, in many people selling or buying products, or even a group of students attending a class. The example we're going to use today is cars driving on a road. And indeed, this is a game too. As a driver, you would like to get to your destination fast. But it's a game because you have effect on others. Cars driving a road also cause congestion, and congestion slows down other players. So let's look at this at a very simple example. So I'm going to think of a case when many travelers want to go between two nodes, maybe from A to B. And there's a very simple little network connecting them with additional cities or nodes C and D. Some highways are just going to think of as broad, big highways. There is no danger of congestion. Unfortunately, they take quite a while. Like in the example, the road from C to B has this property. It apparently takes 55 minutes, and it's not sensitive to congestion. No matter how many cars drive there, or at least within limits, it takes 55 minutes. Similarly, from A to D, in the example, A to D is a very fixed highway. It takes 55 minutes no matter how many cars drive there. In contrast, you want to think of the other two edges on the example graph, A to C or D to B, as nodes that are narrower. They're like short, but very congestible. And what I want to think of there is a road that gets easily congested. If X cars drive on it, then it's going to take X divided by 10 minutes. So it's really fast when X is small, but it gets slow relatively fast as more and more cars drive. So X denotes the number of cars that go from A to C, and Y denotes the number of cars that go from D to B, and each of them have a travel time in minutes expressed as the number of cars divided by 10. So this is just an example, and more generally think of this as a more complicated function, but a function where the number of cars, that is the amount of congestion, is negatively affecting the travel time. The more cars drive, the slower it gets. So X over 10 and Y over 10 are very simple examples. So let's think of maybe 500 travelers that each want to go from A to B, and they all stand at A and wonder which way to drive. So let's start with some very simple examples. So for example, they could all choose to go through C. Every single one of them might go A to C to B. If they do that, then X, the number of travelers A to C, becomes 500, and the travel time on the A to C edge becomes 50 minutes. And so a total of 50 minutes for one edge and 55 minutes for the second edge. That's a total of 105 minutes. Okay, not so great. Alternately, they, of course, could do the other edge. They could go from A to D to B, every single one of them. And that's equally bad, 55 minutes for the big highway. And then this time Y became 500 because all 500 of them traveling from D to B. And that's a total of 50 minutes on that edge and a total of 105 minutes. So if I want to think of this as a game, I should conclude that these players don't have a dominant strategy. Neither strategy is better necessarily than the other strategy. If all 500 people are doing one road, then I, as one of the players, would prefer to do the other road. The other road becomes faster because that one is not congested. In a game with no dominant strategy, we naturally want to think about Nash Equilibrium. So the Nash Equilibrium in the game, again, is 500 players, 2 strategies for each of the players. Either they drive through C or they drive in the other direction through D. And the Nash Equilibrium for this game of 500 players with 2 strategies each is that 250 of them go one way and 250 of the other way. They nicely split the traffic. This way, both X and Y, the amount of traffic from A to C and the amount of traffic from D to B becomes 250. So the travel time in both options is 250 over 10. That's 25 minutes for the more congestible road and 55 minutes for the highway, for a total of 80 minutes, much better than if they are following the same path. And indeed, this is Nash equilibrium because the two options are equally congested. So, choosing one option doesn't necessarily help compared to going over to the other option is actually not making things better. So this is a Nash equilibrium. In fact, this is the unique Nash equilibrium. We can try to think of Nash equilibrium as, some X players choose one strategy, say the AC-B option, and Y players chose the ADB option, and then indeed X and Y players go on the respective edges. We need to have that X plus Y equals 500 because there were 500 players in our traffic example. And in order for this to be equilibrium, it should be that the two paths are equally good. That is, the players on choosing one strategy won't wish to switch and use the other strategy instead. So we want it to be the case that the delay on one path, which is X over 10 plus 55, is the same as the delay on the other one, which is 55 plus Y over 10. So X must equal Y, and as a result, they should be both 250, and that's the unique solution here. So what I did so far is introduce a traffic game. Traffic game consists of players who are drivers. We phrased it right now in terms of driving cars, but if you prefer, there are other things that you can think of, and more dominantly making packets on the internet. While you're not necessarily packets don't make decisions the way car drivers do, they also do get forwarded along edges, and also the system is trying to minimize the travel time, and similar to car traffic, they do cause congestion. Congestion slows down travel time. We assume that every player's goal is to minimize travel time, so the utility is, if you want to express it that way, is the negative of the travel time. The goal in the game for the players is to minimize travel time. We also assume that travel time is a function of the number of other users using the edges that this particular user is using. That is, it's a function of congestion. And of course, it's an increasing function. The more congestion, the slower they can drive. I introduced all this in a context of a very simple graph, only consists of 4 nodes, and assuming all the players want to go from A to B. But what we have done similarly extends to much more complex graphs and populations where they don't all want to drive from between the very same destinations.